Good afternoon, everybody. Welcome to another session of Samvad Talks. The upcoming session of Samvad features the works of research scholars of IIITB who have won accolades for their research in prestigious conferences. Today, we have Rahisha Thotolil with us, who is pursuing PhD under the supervision of Professor Uttam Kumar, who's also here, in spatial data science from Spatial Computing Laboratory. Rahisha won the Best Paper Presentation Award under the theme Spatial Informatics in Urban Planning for her paper titled Quantitative Assessment of Urban Road Network Hierarchy, Topology and Walkable Access using Open Source GIS Tools in the annual conference on Infrastructure and Built Environment towards Sustainable and Resilient Societies held at IIT Kharagpur. Her research interests are AI and ML applications for spatial problems, urban sprawl, spatial pattern recognition and modeling, environmental and natural resource management, transportation modeling, multi-source and multi-format data handling, remote sensing and GIS, and also digital image processing. Today, Rahisha will be talking about geospatial technologies for urban studies. We are all aware how urbanization has stressed the Earth's surface. Understanding the existing road network and building infrastructures is essential for planning development efforts and for understanding the spatial distribution of human settlements. Rahisha's talk today will cover some of these issues. The talk will be approximately for 20 minutes, followed by 10 minutes of Q&A. So without any further ado, I'll hand it over to you, Rahisha.
Thank you so much. Thank you so much for Samvad team for considering us to present our work here. And as Ritika mentioned that my major work involved urbanization issues and civil engineering problems and how to resolve these kind of urban challenges by using geospatial technologies. So before starting with coming to the main topic, I'll just have few words about our lab. I am from Spatial Computing Laboratory. You all may know about it, and this is a part of Center for Data Science. You all may handling with different kinds of imagery, CSV table, kind of a CSV data format and all. How it is different from us, we will handle more into geospatial location data. The data handling location information, if it is geographical coordinate systems are involved within the data set, we call those data set as a spatial data set. So we used to go for different, conduct many workshops, and we used to promote our what are the work we are doing within our spatial laboratory. So we had a lot of conferences, workshops, and many other gathering within our community. So for today's presentation, I'll more focused on urban challenges, that too in transportation problems and urban infrastructure, kind of a building footprints or a building infrastructures, and how these kind of geospatial technologies, kind of GIS or cloud computing, can be helpful to understand, to map these urban maps or urban features, and how to come up with a kind of a decision-making tools. So these are the major content for today's session. So we all know that urbanization is happening very rapidly. That means more people are living in urban area rather than rural area. Then it can be due to simple migrations, or it can be due to the natural increase in population, right? So we all know that urbanization happening. So we cannot do any. How this technology can be helpful to make the urbanization or make the urban planning more sustainable way. That's what a major concern about my research. And UN studies are saying that by 2030, more than 77% of global urban population will be living in developing countries like India, China, or in Africa. So we heard about sustainable urban planning and all. So that means this rapid demographic or a rapid population, urban population, it can be like the spatial transformation, nothing but the extension of urban area. So it is difficult for cities, kind of a small and medium-sized cities, to cope up with all the challenges. So what are the major challenges? It can be challenges. Slum growth can be the resource scarcity can be happen, or it can be due to some kind of environmental problem, climate change can happen. It's all due to the after effect of the unplanned development activities. So my major talk will be we know that this is happening, right? So major features, urban features, are transportation infrastructure and building constructions, right? Construction activities. So the part one of my research concentrated on urban transportation infrastructure, that too in road network. So the major overview of urban transportation, we all know that if you have a very good transportation system, it is easy to move from one location to the other location, right? We all we are familiar with the Bangalore problem, traffic congestions. We know that a lot of road networks are the density is more in Bangalore city, but still we are facing a lot of traffic congestion issues, right? So why this is happening and which are the area it is majorly happening? So that was the major concern with the first part of our research, and understanding the existing system. That is existing transportation. This is more into why these kind of research is very important in current situations. So if while seeing the road network, we can see that it is completely dense. Like if you have the maps, you can see that it's completely dense. But if you have some quantitative measures, you can see that you can compare the result, right? If you have a city map of transportation, like a map of Bangalore and a city map of transportation maps of Hyderabad, while seeing, you can see that, okay, there is some gap. So there is some free space, but how to quantify that? For that, we are using some kind of a spatial matrices to compare it. And major motivation is that ever increasing demand on physical infrastructure of a Bangalore city, it will be useful to study spatial pattern of a transportation system. So instead of talking a lot, I just so here you can see this is a transportation network, okay, road network, simple road network. We can relate these kind of studies into graph theory. You can convert these simple vector layer into a graph. That means every intersection points, dead ends, we can consider it as a nodes, and road segment we can consider as the edges. So this we can completely relate it to graph theory. So this is actually how we are considering transportation network into a graph matrices. Then here this is considering as a pattern. Pattern in the sense here you can see it's a completely grid kind of pattern, right? So it's completely connected. So if the vehicle is traveling from this to end, the vehicle have a path to travel around this. They can move. So, but in case of here, there are many kind of dead ends. But in here, this is a linear, okay? And this is called a tree-like structures. This is called as a different pattern of road network. So that will be one consideration. Then, so initially our study is focused on BBMP area. So BBMP covers around it's across 198 watts. Here, each watts are marked as a different colors. Then individual watts we have considered. You can see this is a Kempegowda watt. It's a watt number 1. So then this is a watt number 84. Like that, we have considered all the 198 watts. Then administrative boundary, we got it from KGIS website, and the road network from OSM. That is the only open source of data source we are getting for a road network. Okay. Then we are considering OpenStreet maps here. Then you can see when you see a small the detail micro level, you can see the entire roads are already digitized properly. When compared to Google Map, it's not updated as it is, but due to the existing availability of freely available data source, we are considering OSM here. Then here, how the graph theory works, you can see this is a two different graphs. When two graphs are considered, we consider it as it's completely planar graph, two-dimensional graph considering, and P is equal to 2 here. So only the simple calculation we required is we want to identify how many road segments are there, how many nodes are there. So when you see these kind of parameters from the network data set, we can directly calculate the circuitry measures, or even the kind of a spatial matrices. It can be alpha, beta, gamma. A lot of matrices already existing from 1960s onwards. These kind of studies are there. And you can see these are the few matrices in case of connectivity measure. The connectivity measures will talk about how well the road networks are connected. But when case of coverage measures, it will talk about how dense it is. Even if it is a tree-like structure, if there is lot of road segment, the coverage will be more. But the connectivity may not be as how it is connected. So these are the measures we have considered to understand the density measures and connectivity measures. We calculated individual ward wise. This is a ward area number of simple open source GIS software we have used to quantify these parameters. Then we got this result as, so you can see the graph pictures here. The center part of the BBMP area are more connected. You can see the light color. So there's the outer side of the BBMP area having less than, the value of alpha ranges from 0 to 1. That means if the measures are more than 0.8, we can tell that those wards or those areas are well connected. So this is how the connectivity measures. This is more related, like up to alpha, beta, gamma, and GTP are more related. We don't need to consider all the connectivity measures. We can consider with only one matrices, talk about which are the areas are well connected. And this paper we published in INCARS 2021, and the studies shows that out of 198, only 25% of the wards are well connected. More than 164 are less connected. Okay. Then we considered what is the relationship between the coverage measures and connectivity measures. Then why we are doing this kind of relational study? We want to model it. If we have it, because when we give the road network, we can easily quantify the density measures. We have the total length. If we have the steady area, we can easily calculate the density as a total length of a road divided by area. Okay, that will give you the density measures. If you are having the density measure, is it possible to calculate connectivity measures? That is why we are modeling it, right? So when we have, our model says that if you have a net edge graph density or nodal graph density, you can predict eta index. That is also one matrix that talks about what is the minimum size of a road. So that can be around 0.81. Then, okay, with that, this was the previous year's work, 2021 work. So we want to extend our work with a grid-based analysis, because always the road networks are not within the limit of a ward administrative boundaries. We can look with a grid-based analysis also. So for that was the paper we presented in IIT Kharagpur, and we got a best paper presentation award. And from Springer, we got a gift voucher of €200 for purchasing ebooks or any kind of academic papers. So extension of work is talking about, because initially we considered all the 198 wards. Right? So now we are looking only HSR layout where I stay. So this is HSR layout. Is a 174th ward, and we have considered one grid, 30 square kilometer grid like this, and we consider 1 square kilometer unit grids here. Then we want to see individual grid. We want to analyze micro level analysis. So in that case, so apart from connectivity and coverage measures, what are the other quantifiable measures or other matrices required to do kind of a transportation problem? So we come up with one paper published by IIHS. So they have developed a plugin, Coins. So what they can do, if you have a kind of a road network, it is not a classified, it is a simple vector layer. So if you have a GIS software with a Coin plugin, so we can see that which are it's a kind of a classification of road networks, types of road networks. We can see that the Coins results are giving like this, right? So this is the major road length. So initially when you want to digitize it, and you have to name that, what is the type of road? Instead of that, the software will give you based on the stroke length. I don't want to get in detail about the technical aspects, but the result will be, you can directly what is the major type 1 classes, type 2 classes, type 3 classes. Up to you, how many type of classes you want to classify from the transportation network. So this is what we published. And another work is, when you see a grid level, in which grid having a major problem, in which location the connectivities are more or connectivities are less. So you can see the two measures. Alpha index you can see here. You can see this is a completely nearly water body. There is no road network. Because if there is no road network, connectivity also will be very less, right? So if you have a segment of road, then it will be a connectivity will be very less. That means this area having a 0, all those 0 values. But when you see the network density here also, road networks are total length of a road is very less. That is why it shows the connectivity is less. So apart from these hierarchical map, that is called a type of maps, or even the connectivity coverage measures, we are more concentrated on walkability also. Suppose you want to open a new shop, and if you have a building footprint maps like this, is it possible to locate which grid will give you more walkability? That means if you consider these green grid, these are the grid have a more number of shops or more number of buildings, I'm considering the center, because right now area of interest is I'm considering just a center point of a grid, then considering that which grid is having a more accessibility in the measures we are considering by, we are calculating by measures. Can see the values here, walkability access measures. So this paper got awarded for a best paper, because right now most of the work is happening through they are going to the field and they are identifying some location which is very congested area, and now identifying number of vehicles passing through this. So this is not a realistically possible, right? Because if we see it only for HSR layout, just 30 square kilometer, if you want to do such a in detail like ground based studies, it need more than maybe a 6 months, 1 semester is entirely dedicated for these kind of research. Instead of that, geospatial technologies will give you a better understanding or calculating these kind of measures in one platform actually. Okay, so this is a very important work for any kind of a transportation studies. And you can see from here which grid, so exactly in which location walkability is high. So this is one study, and extension of work we are considered, because that is only HSR layout. Right now, when you see entire BBMP area and more than that, if you want to create a hierarchical map of transportation, it is not an easy task. You want to understand which are the major roads, because OSM is not giving the type. So, but these kind of geospatial tools will help you to understand which are the major. Maybe in future, if your research is more into only highways or only streetways, you can extract only those data set from this huge database. We don't need to work with a complex road network from here. So, okay. So this is grid based. We want to extend it in for the future studies. Okay, with that, I'll conclude, because the part 1 is more into transportation problems, how we can do these kind of geospatial, how we can use these kind of technologies to resolve real world problems. Okay, then major, because I'm a civil engineer person, I don't want to focus only transportation engineering. I'm more into construction activities, how the building footprints are, because mapping individual footprints is not an easy task. Digitizing individual footprints is not an easy task. So how to automate it? Because I'm from IIITB, I have to work with the machine learning approaches, deep learning approaches, and what is the real-time technologies. So with that, building footprint extraction using machine learning algorithm called random forest classification. So here again, my study area is HSR layout. So this is HSR layout what? Sorry, here this is HSR. Pointer is not working, but you can see that this is around 7 square kilometer. Then to understand the to know the footprint, we need a very high resolution satellite imageries. So right now I am using only Google Earth imageries. That means it's only a JPEG or a RGB imagery. We are not looking for a multispectral imageries for the first studies. Then what we have done, we have clipped a study area with equally sized imageries, and manually we have done the ground truth, manual digitization of building footprints. Then we come up with a model. So you can see this entire building footprints are manually extracted, manually digitized by myself. Then we have a vector layer, and we have a imageries of a symbol Google Earth imageries. Then we come up with a model. We can just convert it RGB into gray, because we are not working with any kind of a spectral like a near infrared radiation like a spectral bands right now. So what we have done, we have used mathematical morphology to extract the boundary or extract where the higher reflectance of building footprints are there, and we have come up with RF classification method, and these are the maps produced by our model. So if I need to explain further with the one model, I can explain it, but I just want to showcase what kind of work we are doing within our lab. Okay. So this is how the classification methods, the building footprints shows. I'll show the result here. Here, this is the first column is talking about our result. When we do little bit of post processing, we can improve our result by 85.62%. This is completely ground truth, manually digitized, but still you can see that it is 85.62% more, around 86% footprints are easily extracted completely from the free tool, free software, and a free data set. Google Earth imageries are a simple free data set. So this work we published in Connect 2022. Okay, extension of this, because till now we are not working with spectral bands, right? Right now we are more interested if you have a spectral band, how the result can be. So that we presented in SPP student poster presentation. We won first prize. So I'll just tell you how it is different from the previous data. So this is called a multispectral data. That is what we are expert, right? Remote sensing background. So here we are not even handling RGB bands. We are handling near infrared, all the shortwave infrared, different multispectral bands. But right now, Worldview 2 is a high spatial resolution, but with a 4 bands, only near infrared. Okay. So here you can see this is called a false color composition. So you can see wherever the bright colors are there, cyan colors are there, that is representing building footprints or a buildings. So we have modified our model. Okay, little bit modification has done. So the result shows that if you have a simple morphological operations, still we can extract some kind of a features. Buildings can be extracted from here. You can see here that gray, the little bit darker color shows the higher the presence of buildings. Okay, then the result shows that without, because initially we consider a lot of features, because resolution wise it is high, but the feature wise, number of band wise, it is very low. Because of that, here we are considering less number of features with a higher resolution. Spatial resolution is very high and spectral features are less. You can see simple grayscale image and a ground truth. You are able to predict by using simple CNN method. You are able to predict 93.52% of accuracy. But the problem, the satellite image, these kind of satellite imageries are not free of cost. We have to procure from foreign organizations or even ISRO. So up to that as that. Then now my future work, like what we have come up with a footprint extraction, road network analysis, and what is further? What we can do further? From IISc, Uttam sir's and then under TVR sir's lab is doing a lot of study on LUSC mapping. That is nothing but land use, land cover change. 10 minutes. Yeah. Yeah, okay. Yeah. So this is how this, from the satellite imagery, you can see 1973, it was completely green city. It's complete, only very few part was a buildings, okay, or a built up area. So when you see 2020, it's a completely concrete city. Now we can call it as a concrete city. So only through satellite imagery, you can classify these kind of informations. So with that in mind, we have done ward level LUSC mapping by using cloud-based Google Earth imageries. That means we don't need to download any kind of a satellite imagery. The computation, data analysis, pre-processing, everything will be done in the Google Earth Engine platform. So I'll just show you the result here. You can see this is 2018 and 2020. You can see only 2-year period. But you cannot, by manual interpretation, you cannot see exactly where the changes happened. So when we see ward level zonal statistics, we can see most of the ward has increased more than 6%, 8% increase, the urban area is increased. So we thought, is there any problem with our model? So we come up with a Google Earth like evaluation. Whatever work we are doing, we have to evaluate our work, right? So in that case, we come up with the Google Earth maps. 2018 image, these are the 2018 imageries and that are the 2020 imageries. Within 2 years gap, you can see that there are a lot of buildings are pop up. You can see this construction. This is a lot of that. I just highlighted only few part. So this is what, and more than one, like around 173 watts has increased the built up area. So with because we have the platform, we have the very huge cloud-based platform. So we want to do a electricity, like which are the area does not have electricity. So this is our entire study area we consider. I'll just come. So this is the nightlight imageries. This is also a very good database which is freely available through Google Earth Engine. So you can see this is LULC map. This is called a multi-class LULC map. You can compare it, which are the area does not have electricity. So the research shows that in our study area, around 6.8% of the pixels or the area does not have electricity. This work also we published in INCAS 2021. So the further will be urban growth model. So when you want to predict something, we should have a very historical maps, right? We have a 1973 onwards, satellite imageries are available. We can create a land use land cover. How we can do much further? Then for that, urban growth model will help you. Cellular automata is the 1980s onwards. These kind of models are available. Different. I'm not putting any statistical measure here because these works we didn't publish. So these are the LULC map, different models, different, and we want to. This is the latest 2021 plus model. Then future is more into national level project because we don't want to focus only metropolitan city. Indian government is come up with many kind of schemes called integrated development scheme called medium and small sized city development. That means they are ready to fund these kind of small and medium towns for any kind of infrastructure facilities. First task is identifying those cities. We identify such cities and we have analyzed transportation infrastructure, and we can give a suggestion to the government that which are the cities should have transportation fund. Like if the local government is asking fund to the government can take a decision that if the city is already well developed to the transportation, stop funding only for transportation, fund for something else. So these kind of a development scheme, our research will be more focused on decision making for the government. And by using generative model, we can develop kind of a future human settlement, and we can predict the transportation matrices, how the transportation matrices should be there for the future cities. So that is what the current and future work is going on. I think I had taken 5-10 minutes extra. Thank you so much for listening, and I can take some questions.
Thank you, Rahisha, for this presentation. Now it's time for some Q&A. So is there any questions?
Thank you. Very good body of work.
Thank you, sir.
In the last slide, you mentioned about GAN, right? So you're trying to make some predictions, right? Is it about predictions of future growth type of thing, or a generative model?
Actually, this is not a prediction because we cannot predict for a future. It is a simulation model. So that means if we have IDMST project will fund for the population is belong to up to 5 lakhs. So we identify such cities, and global urban footprints maps are freely available. So we identify those binary imageries for Indian cities. Then we got around 505 cities such. So with that 505 cities, so we are telling that future will be like future in the sense, if the population belongs to this range, then we can simulate the there's a human settlement map. We can call it as these binary imageries are human settlement maps. We want to produce it through generative models.
So it's like a conditional model, is it?
Yeah. Just like we have a data set, then because we got inspired from this computer vision papers.
Understood.
Yeah.
And the first line of work, walkability and stuff.
Yes.
So do you have some validation data there?
No, right now we don't have a walkability. Only we can do by seeing the picture very carefully. We didn't go to the ground and we didn't see that. But the problem is that one grid, we could see that number of building footprints are much higher in that area. Obviously, in that area, if you are opening one shop, there are major shops will be very close to. So that is the only concern we consider at this moment. Ground observation is not yet done. Actually, one of our professor from IISc, they are doing a ground observation. So they approached us to just see how the results are matching or not.
That will be good, right?
We are planning actually.
Yeah, thank you.
So Rahisha, I presume that these data sets are very large images. So I was wondering if there is an algorithmic aspect to this research, in the sense, can you design your algorithms in such a way that they are more performant, or they take less space, etc., etc.? Is there such an angle to your research?
Right now, no, because for me, algorithms and models and all, I'm very scary to touch. But what we did, because satellite imageries are very huge, and we have converted, or we have considered some kind of a machine learning model to prepare LULC map. Then LULC map will consider only one band, or it will be one band. So we don't need to work on all the 11 bands. So now, once the classification is done, the model will be taking care of LULC map. That won't be very spatial, like the space will be very less in that
So
case.
you can run them on normal commodity machines like this.
Yeah.
right?
Yeah, because we are doing with the individual level, even though we are working with 33 years of data, but we are working with every year we are doing a different model for a classification. So with a 1 year, we can run it through our system. But for a GAN model, we need a very high supercomputers or a server support. But in our lab, we have that support. Like we have the capacity to run. Server support is there within our lab.
Another minor observation was in the first part, where you were talking about graphical models. You mentioned that those are all planar models,
Yes.
but when you have flyovers and stuff like that, it won't be a planar graph anymore, right?
Yes, it is not. But to do these kind of studies, right now we are assuming that it is a planar graph, like a 2-dimensional format. But if you want to do it the 3-dimensional, this kind of a graphical, we need a higher quantification matrices for a 3-dimensional transportation matrices. But the papers were very less. Only 1 or 2 papers I come up with a 3-dimensional one, but they have come up with from the scratch, they build a model. Right now, I'm not building any kind of a matrices. Existing matrices, I'm just evaluating how the Bangalore transportation is varying among wards or a grid wise. I'm doing that. So that is a very good input, sir, because if we want to work on 3D reality, we have to work with the subways, bridges. That consideration should be there. Because our graph will say that the transportation is well connected and the roads are there, but maybe that will be flyover. So that may not be connected exactly through the service, or that this is need to be. Yeah. Thank you, sir. What do we have?
So on the same lines as that of the graph, wanted to understand when you took them as a graph nodes, right? You would have also created the vertices for each one of them to connect them. But what was your field of view to say that, okay, this matrix will hold for these kind of roads?
So can I come? Yeah, here, right?
Yeah, I mean, I think the previous.
Yeah, here.
Yeah, here.
So what, so your question was how the matrices will be evaluated based on this graph?
Not only evaluated,
Hmm.
how did you construct it? Because the images may be of a different field of view.
No, it is not from imageries. This first part of our project was related to vector data model. It is a completely one layer. It is not from imageries.
Okay.
And we got a data set from OpenStreetMap. They are giving digitized road network. We are not manually digitizing it.
Okay.
So this is a completely vector layer, because spatial data can be represented in 2 formats. That is, one is vector. Any interest can be represented as a point, line, or polygon. Then right now we are looking at the line features. So this is not from imageries. I got now your, because if the road length, if we are digitizing it, then the perspective from which angle the camera has taken, that need to be taken care. But that will be considered for automatic road in extraction models. But in our case, we are ready-made available data set we are considering. So then we are considering the entire, because that is entirely planar graph. They are not taking any kind of attribute information with a height or a depth. So right now it's a completely a 1-layer graph. we are converting that into, see, little bit pre-processing is required because some cases it won't be joined in reality, but little bit pre-processing is required. Then after that, so we will be converting to network data set. This is before network data set, we cannot identify which are nodes, which are edges. When we convert the graph in simple line features into a network data set, exactly the dead end points or intersection points, the nodes will be generated. So we can easily identify how many nodes are there within that area. So that will give you one variable. So like the number of edges also easily quantifiable. If we have a edges, total length of a road, if we have a number of nodes, we can easily calculate alpha in text by using these equations. So you can here, the first that is also giving the transportation matrices talking about connectivity.
Yeah.
So alpha is calculated by E minus V plus P. P is nothing but right now we are considering a one graph. P is equal to one.
Okay.
If you are looking with that word number 1 here, word number 2 here, if you want to do the connectivity measures of word number here and word number, P should be 2.
Okay.
Right now we are telling that one word. So P is equal to 1. So then it is easy to calculate alpha. Then when we calculate alpha, the value will be range from 0 to 1. Then if it is a 0.8, then we can tell that it is well connected. That means circuits are more into that area.
I see.
When you see a tree-like structure, alpha value will be 0.4, 0.3 like that.
Yeah, okay. Got it.
For a 1 or 2 graph, we can easily tell that, okay, this is well connected. But when you do a 198 watts and that too very complex road network, it is not easy to tell that which ward having well connectivity. Only these kind of a quantifiable measures or a matrices can help you which are the wards having well connected measures.
Thanks.
Thank you so much.
We have one last question which we'll take, and after that we'll call it a day.
Initially, you talked about the general challenges of urbanization and such. Then we looked at a lot of data and analyzed it, like connectivity, coverage, and but what you observed is generally where there is high connectivity, there's also high traffic. So, like looking at all this kind of data, whatever you talked about, what are the kind of policy recommendations we can make, like in terms of, say, build infrastructure here, don't build here, build metros here, or even zoning laws? Like, how can this data be used?
Thank you. Very good question. So what initially we want to understand what is the current scenario, what is there in existing scenario. Then right now we are not looking with the other data set, like any other population density can be a problem, number of bus stops can be and one. These are called driving factors. Because connectivity is more in the sense it's not related to, even you are telling that still the connectivity is there, but still the traffic congestion is there, right? So we have to look for number of vehicles passing through that area. So many other driving factors required to analyze individual ward or individual area to take a decision. This is happening because of this. So right now, we don't know why this is happening. We are telling that this area well connected, but still if the congestion is there, some other problem. So you have to come up with like we have to do a further research that in reality, why the center of the city having still the traffic congestion. Silk Board having because Silk Board is still because I know few bottleneck points in Bangalore. So when I was checked with the Silk Board, connectivity is not very high in that area, but still the traffic congestion is very densities are more in that cases. But density cannot be directly related to traffic. Okay, and many other factors can be because real land use, land cover. If the vegetation is more or the water bodies are more, connectivity will show less. It doesn't mean that there is a very congestion problem. So there are many features. We have maybe future research. We have to look further. Thank you.
Thank you, Rahisha, and thank you everyone for coming. Also, we apologize for the delays and the technical pitfalls that we had. We'll look forward to seeing you again for the next session of this particular series, and there we'll be having Nithya with us, who'll give us a talk. Thank you once again.